This week we're going to be reviewing linear functions. Specifically, we're going to go over rate of change or slope, the independent and dependent variables, and using slope-intercept form to model real-world situations. So let's get started. The rate of change. So many of you know what the rate of change or slope is. It's usually denoted by the variable m. All right, and we refer to the concept by saying slope or the rate of change. Now, you may have learned that to identify the rate of change, you use rise over run. All right, I particularly don't like this little mnemonic or way of remembering it because it gives you the false impression that the numerator and denominator are always positive, because when you rise, you're elevating or increasing values, and when you run, you usually run forward. But this is not actually the case. A more precise definition of slope, or the rate of change, would be the change in y over the change in x. And as we'll see later on in this lesson, all right, what this really means is the change in the dependent variable, or the output of a function, over the change in the independent variable, or the input of a function. Now, these concepts are usually or often referred to by this little Greek symbol delta, all right? And delta just means the change in. So if you see this little triangle, it's delta. We might read this as delta y over delta x. And to find the change in two values, all you do is find the difference between its ending point and its starting point. So you take away the starting point, or the first y value, from the second y value, and you do the same for the x's. So although all of this is important to understand, the only thing you really need to remember or memorize is this little formula: m equals y2 minus y1 over x2 minus x1. All right, so let's try using the formula to calculate the slope of lines passing through these points. All right, so this is just a little refresher on how to use this formula. Why don't you pause the video and try to calculate these three slopes now, and we'll return in just a few seconds, or after you're done, to see how you did. Pause the video now. All right, let's see. So for number one, what I suggest you do is either make a mental note, or you can mark what each number in each ordered pair is. So like, for example, this is our first ordered pair, this is our x value, this is our y value, this is the x and y value of the second ordered pair, so we might want to call this x1 and y1, which is the x value of the first pair, y value of the first ordered pair, and so on and so on. So now we can just plug these values into the formula. So since the formula is y2 minus y1, we would write 12 minus 5, and then x2 minus x1, that would be 6 minus 2. And so you should have set up your formula like this, and simplifying these expressions, you get 7 over 4. So the first slope, or rate of change, is 7/4. All right, let's go on to number 2. Again, this is x1 and y1, x2 and y2. All right, plugging these values into the formula, what we'd get is y2 minus y1, or 9 minus 0, and then x2 minus x1, which would be 3 minus negative 4. Now when you write that down, it looks like this: 9 minus 0 over 3 minus negative 4. This is important because here we have a double negative. We're taking away negative value, which is analogous to addition. So instead of thinking of this as 3 minus negative 4, you might want to think of it as 3 plus 4, which is how we get our 7 here. And of course, 9 minus 0 is 9. So the rate of change, or slope, is 9/7. And for number 3, we've got x1, y1, x2, y2. All right, so plugging the values into the formula, we get negative 2 minus 10, and negative 1 minus negative 5. Now writing that down, it looks like this: negative 2 minus 10, negative 2 and negative 10 make negative 12, and negative 1 minus negative 5, all right, is really negative 1 plus 5, which is positive 4. And negative 12 over positive 4 reduces to negative 3 over 1, or just negative 3. Now, sometimes ordered pairs are organized in the form of a table. So what I'd like you to do is try calculating the slope between the ordered pairs that are shown in the table. There are 3 sets of ordered pairs: 4, 1, 7, 7, 7, 7, 13, 19, and 13, 19, and 17, 27. Pause the video and try to do that now. All right, let's see how you did. So for the first one, 4, 1, and 7, 7, we plug that into the formula, and we get 7 minus 1 over 7 minus 4, which is 6 over 3, which reduces to 2 over 1, which is just 2. For the second order, set of ordered pairs, we have 7, 7, and 13, 19. y2 minus y1 is 19 minus 7. x2 minus x1 is 13 minus 7. And that would get us 12 over 6, which is also 2. And then we have 13, 19, and 17, 27. Plugging our values in, we have y2 minus y1, which is 27 minus 19. x2 minus x1 is 17 minus 13. And that gives us 8 over 4, which also reduces to 2. Now, since the rate of change of this table is constant, we can probably say that it's what type of function? If you said linear, you would be correct. Now, using the formula is a very useful tool, especially when you're working with raw data. However, when the information is organized in a table, you might want to try just looking or mentally calculating the difference or the change in the y's over the change in the x's. So you could try something like this. 1 to 7 is a change of 6. 7 to 19 is a change of 12. 19 to 27 is a change of 8. How is x changing? We're jumping up 3, we're jumping up 6, we're jumping up 4. Now, that wouldn't seem like the rate of change is constant, except you need to remember this basic definition that the slope, or the rate of change, is the change in y, or your outputs, over the change over the inputs. So, what's the change in y here? 6, all right? So the change in y over the change in x is going to be 6 over 3. And here we have 6 over 3. All right, the next change is 12 over 6. That's 12 over 6. And the next change is 8 over 4. And we have 8 over 4. And we know that all 3 values are equivalent because when you reduce all these fractions, they all reduce to the same fraction, 2 over 1. And that matches the results we got here. So the rate of change is always going to be 2 over 1 in its simplest form. All right, independent and dependent variables. So in the context of an experiment, the independent variable is a variable that represents a quantity that is being manipulated or changed. So you might have heard about independent variables in science. And that's a good definition of an independent variable in science. In math, it's related but slightly different. In the context of a mathematical function, the independent variable is a variable which can be assigned any permissible value without any restriction imposed by another variable. Now that is also a very good definition, but it's difficult to understand. So let me put it in student-friendly language. The independent variable is the input of a function. It's what you put into the function. Now, dependent variable, in the context of a scientific experiment, the dependent variable represents a quantity whose value changes in response to how the independent variable is manipulated. Now, in the context of a mathematical function, the dependent variable is a variable whose value is a result of, or that depends on, the value of the independent variable. Or in other words, the dependent variable is the output of a function. So, when making a graph, the independent variable, or the input, is always graphed along the horizontal axis, this one right here. All right, and the dependent variable is always graphed along the vertical axis, which is why the variable x and y always refers to the independent and dependent variable, and why our x-axis is always horizontal and our y-axis is always vertical. Now, here are 4 different situations. What I'd like you to do is read through each situation, and I want you to see if you can identify the independent and dependent variable. Now, because these are real-world situations, there's kind of a convergence of math and I guess you could say science, since we're trying to model the real world. So in the real world, there usually is some variable that causes or precedes some other value. So keep that in mind when you're reading through each one if you have trouble deciding what's the independent and dependent variables. So pause the video now, write down your answers, and we'll see how you do. All right, let's take the first one. John uses the radius to calculate the area of a circle using the formula A equals pi r squared. So when you're given an equation, identifying the independent and dependent variables are pretty simple. Since the dependent variable is the result of the independent variable, the way this equation is written, the output here is A, the area. So the dependent variable would be the area of the circle, and the independent variable would be the radius. And you can think about this if you used a geometric compass, right, to draw a circle, and you increased the radius, well, then the area of the circle that you're constructing is going to be larger. So the length of the radius is the independent variable, and the area of the circle is the dependent variable. Next one, the relationship between the average engineer's salary and how many years of higher education they attained can be modeled by the following equation. Again, equations are simple to analyze because the output is usually pretty clear. All right, the output here is y, and the input here is x. And since I told you that x and y are usually associated with the independent and dependent variables, it should be pretty easy to see what they are, or what means what. The only thing you need to do is figure out, in the context of this situation, what does x represent and what does y represent. So let's think about this, this causal relationship. What depends on what? Does the engineer's salary depend on the level of education, or does the level of education kind of affect how much an engineer is paid? So I would say that the years of higher education would affect how much an average engineer would be paid. Next, David measures the height in inches of his tomato plant every week. This one's a little less clear. Does the height of the plant affect the time that goes by, or does the time that goes by affect the height of the plant? Well, since plants grow, throughout time, and you can't really stop time. Time is very often the independent variable, although I should say it's not always the independent variable. So you can imagine an experiment where you're given some runners some Gatorade and other runners water that looks like Gatorade, and then some other runners just water, and then measuring how fast they run. In that case, you're going to measure their speed, which involves clocking their time over a set distance. So the data you'd be collecting there is time, and time would be your dependent variable. The independent variable would be the manipulation of what they're drinking before they run. But in this case, time is the independent variable. So the time would be the independent variable, and the height of the plant would be the dependent variable. And finally, Mark works full-time as a busboy at a local cafe. Excuse me. He earns $11 per hour. All right, so if he earns $11 per hour, the more hours he works, the more money he makes. All right, so the independent variable would be the hours worked, and the dependent variable would be the total earnings or the amount of money that he makes. So let's do some practice with this. So what I'd like you to do is find the rate of change in some real-world situations. In the descriptions below, identify the independent and dependent variables, write a set of ordered pairs, calculate the rate of change, and interpret it in the context of the problem. So basically, if you calculate your rate of change and it's like 3/4, what does that mean? 3/4 what? What's changing by 3? What's changing by 4? That's interpreting it in the context of the problem. So pause the video, write down your answers, and we'll see how you do. Okay, a climber is on a hike. After 2 hours, he is at an altitude of 400 feet. After 6 hours, he is at an altitude of 700 feet. What is the average rate of change? So to begin our analysis, we're going to identify the independent and dependent variables. So what causes what? Does the altitude cause the amount of time that he's been climbing, or the more time he climbs, the greater altitude he reaches? So I would say the more time he climbs, the higher he's going to get. So the time here, measured in hours, is going to be our independent variable, and the altitude is going to be our dependent variable. Now this is important because it helps us set up our ordered pairs. So we're going to identify 2 points by first identifying the independent and dependent variables, and now we know how to set up our ordered pairs, because in an ordered pair you always put the input or the independent variable first and the output or the dependent variable second. All right, your rate of change is going to be all messed up if you switch these values. So the hours, 2 hours, after 2 hours, he is at 400 feet. After 6 hours, he's at an altitude of 700 feet. So now what we can do is calculate our rate of change using the formula. y2 minus y1 over x2 minus x1. And that gives us 75 over 1. But 75 over 1 what? This is why identifying the independent and dependent variables are so important, because it literally tells you what units or what concepts the rate of change is describing. So remember, rate of change is the change in y, or the output, or the dependent variable, in this case altitude in feet, and the denominator is going to be the change in your input, or the independent variable, in this case the number of hours hiking. So the unit for the for y, or the numerator, is going to be in feet, and the unit for the denominator is going to be in hours. So this would mean 75 feet per 1 hour, or just 75 feet per hour. All right, the second one, a scuba diver is 30 feet below the surface of the water 10 seconds after he entered the water, and 100 feet below the surface after 30 seconds. What is the scuba diver's rate of change? All right, so let's first identify our independent and dependent variables. It seems like we have the depth below the water, all right, and the time that he has been diving. So does the depth depend upon the time, or the time depend upon the depth? Again, this is another situation where time is kind of constant. It's just going by, and the more time he spends diving, the farther below the surface of the water he's going to get. So time is our independent variable, and the depth is our dependent variable. So knowing that is very important, because some of you might have been tempted to just write 30 and 10 and 130, because the grammar or the structure of the sentence has this number first and that number second, this number first and that number second. But if you did that, your rate of change is going to be all messed up, and I'll show you why at the end of this problem. So our independent variable, our independent variable is the time in the water, measured in seconds, right? And our dependent variable is the feet below the water. Now, once we know that, we know what numbers to pair up and how to pair them. All right, so after 10 seconds, the diver is 30 feet below the water, and after 30 seconds, the diver is 100 feet below the water. Using the formula to calculate the rate of change, we have 7 over 2, or 3.5. Now, 7 over 2 what? Now, because our dependent variable is feet below the water, that would refer to 7 feet, all right, every 2 what? In this case, every 2 seconds. All right, and this reduces to 3.5 over 1, or 3.5 feet per second. Now, why would it be important? Why can't we switch the independent and dependent variables here? Technically, we can, and we discussed this in class to some extent. I gave you the example of, why do we say miles per hour instead of hours per mile? Can't tell you. It's kind of, we think of time as being this concept that just kind of goes by, and what we do throughout time is the result of doing things, in a universe that moves forward. Imagine how confusing this would be if the 2 were in the numerator and the 7 was in the denominator. Then that would mean 2 feet per 7 seconds. I'm sorry, no. That would be, what's 2? 2 is the seconds. 2 seconds per 7 feet. So instead of writing 3.5 feet per second, we would have a 2 over 7. That's not a very nice decimal, but it would be 2 seconds per 7 feet. And we don't think of this type of activity in terms of seconds per feet, but rather feet per second, or feet per second. All right, finally, a rocket is 1 mile above the Earth in 30 seconds and 5 miles above the Earth in 2.5 minutes. What is the rocket's rate of change in miles per second? Oh, that should be possessive. That's a typo. Rocket apostrophe S. Okay, so let's see. What is our independent and dependent variable? All right, so again, this is time's just moving on. Time is our independent variable, and the altitude above the Earth is our dependent variable. The altitude above the Earth is our dependent variable. So after 30 seconds, the rocket is 1 mile above the Earth. Now, some of you might have put 2.5 here without realizing that you need to keep your units the same. All right. Whenever you're working in math, you have to convert your units, so you're working with the same units, or you're going to get all mixed up. This is not 1 and 2.5. I'm sorry, this is not 30 and 2.5. It is 30 seconds and 2.5 minutes. And 2.5 minutes is 150 seconds. So, after 150 seconds, the rocket is 5 miles above the Earth. All right. Calculating our rate of change, we get 1 over 30, or approximately 0.3, and that would be 0.3 miles per second. And why? Because our dependent variable is the altitude measured in miles, and our independent variable is time measured in seconds. So this would be miles over seconds, or miles per second. And finally, using slope-intercept form to model real-world situations. So we're all familiar with slope-intercept form. Y equals mx plus b. Let's quickly review what each part of the equation means. X is our input, or our independent variable. Y is our output, or our dependent variable. M represents the slope or rate of change. And B is our y-intercept, which is, or can be thought of as kind of like your starting value or your starting point. Because basically we're taking B and we're adding a value M X number of times. So we start with B, and then we're going to add M. And how many times do we add M? Well, this is multiplication. We're going to add it X times. So that's why it's kind of like our starting value. Okay, in order to write a linear equation in slope-intercept form, you must first identify the slope and the y-intercept. And that's all you need, because you can identify your input and your output, because what you're trying to do is write a model for many inputs and their respective outputs. So, let's take a look at the following situation. A puppy weighed 9 ounces at birth. It gains 5 ounces each month. So how are we going to write this? What's the rate of change? And what's the y-intercept, or the starting value? Well, its starting value, it started at 9 ounces at birth, and it gains 5 ounces every single month. So the first month, 5 more ounces. Second month, another 5 ounces. So that is its rate of change. There's our rate of change. There's our starting value. So what we can do is write our little equation. Once you have these two values, you can write a linear equation. Y equals 5x plus 9. And all we did was plug in our rate of change and our y-intercept in the proper place in the model, and we've modeled this situation. Now, I want you to notice how the rate of change reveals the dependent and the independent variables. So if you're given a situation like this and you want to identify what are the independent and dependent variables, well, this 5, all right, written as a fraction is 5 over 1. Now we know, all right, that since this is 5 ounces each month, all right, that ounces is our numerator and month is the unit of our denominator. And we know that the numerator is just the change in y, or the change in the output, or our dependent variable, and the denominator, or the input, is our independent variable. So we know that months, or time in this case, is our independent variable. Time seems to be an independent variable a lot. All right, so why do we care about this? Because it's often appropriate to incorporate the dependent and independent variables when writing an equation using function notation. Using meaningful variables makes the statement more readable. All right, so rather than just using f of x or some a of b, some random letters, what we want to do is when we want to describe the relationship between the independent and dependent variables. So this is why we say w of m. What does that mean, w of m? Well, in the context of this problem, all right, w is the weight and m is the months. All right, the weight of the puppy is a function of the number of months the puppy has been alive. So w of m, in this case, is kind of a shortened way of saying the weight of the puppy is a result or a function of the number of months it's been alive. And how are those two values related? Well, this is the rule, all right, that tells you how they're related. So given a value m, you can calculate the output w, or w of m. So let's put this to use. For each situation, identify the independent and dependent variables and write a linear equation using x and y as your input and output, and then a linear function using meaningful variables. All right, so here's the first situation. Let's go through it together, and then you can do the next two on your own. So an airplane 30,000 feet above the ground begins descending at a rate of 2,000 feet per minute. Assume the plane continues at the same rate of descent. All right, so we want to identify our independent and dependent variables. We've got, let's see, feet above the ground, and then our rate of change is feet per minute. Now, it looks like this is going to be our rate of change, so our rate of change, or our slope, reveals the independent and dependent variable. Feet per minute means, all right, that feet is going to be in our numerator, minutes are going to be in our denominator, so it looks like the altitude is our dependent variable, and time, measured in minutes, is going to be our independent variable. And there we go. And then once we identify our starting value and our rate of change, we can write our equation. Y equals the rate of change times x plus the starting value. And of course, if we wanted to use function notation, we would write meaningful variables. Here I chose to use a of t, or the altitude is a function of time. You could have used feet, as a function of minutes. Anything you want, just as long as they're meaningful in the context of the problem, and they're meaningful to both you and your audience if you are presenting this to anyone. So let's try the next one. You go ahead and pause the video, see if you can identify the independent and dependent variables, and write these two equations on your own. Oh, pause the video now. So, suppose you receive $100 for a graduation present and you deposit it in a savings account. Then each week thereafter, you add $5 to the account, but no interest is earned. So, in order to begin to model this, let's first try to find the rate of change and the starting point. All right, so our rate of change here, all right, is right here. Each week thereafter, you add $5. Another way of phrasing this would be $5 per week. But I didn't phrase it that way so that you'd have to understand the meaning of the words and not just recognize that kind of something per something language that we usually use to describe a rate of change. So each week thereafter, you add $5. $5 per week is our rate of change, and our starting point, all right, our initial value is that $100. All right, so now we can easily identify our independent and dependent variable. If this means $5 per week, then we know that dollars is our dependent variable, weeks is our independent variable. So you could have described the units or the concepts. The independent variable is time in weeks, and the dependent variable or the account balance is measured in dollars. Okay, and now that we have our two values, our rate of change and our starting value, all we have to do is plug that in. All right, so y equals $5 per week times x plus that $100, or the balance is a function of the number of weeks you've been saving, and that equals $5 per week plus that $100. All right, let's try the last one. All right, a beaker of boiling water is boiling water is 212 degrees Fahrenheit, begins to cool. The temperature drops 11 degrees every minute. So pause the video right now and see if you can identify the independent and dependent variables and write your two functions. Pause the video now. Okay, so again, we're looking for a rate of change and a starting value. Now the rate of change right here, all right, it says drops 11 degrees every minute. All right, this is important because drops tells you that it's not increasing, but it is decreasing. So this is going to be a negative slope. And of course, if the water is boiling, then it has to be at a temperature of 212 degrees Fahrenheit if you're at sea level. So there's our starting point. Now, what are our independent and dependent variables? Again, we look to our rate of change to identify them. If this is degrees every or per minute, then degrees is our numerator or our dependent variable, and minute is our denominator or our independent variable. So our independent variable is time measured in minutes, and our dependent variable is temperature measured in degrees Fahrenheit. I should have specified that. And of course, here are the two functions. Y equals negative 11x plus 212. So y equals negative 11 degrees every minute plus a starting temperature of 212 degrees. And you could have used anything you wanted here, just as long as they're meaningful. And that's it. That's the whole exercise. All right. So move on to the skills assignment and the performance tasks. They reinforce the concepts that we went over in this video.